This is the solution to random MathStat problem number 186. In this problem, we're given a random sample, x1 through xn, from a continuous distribution with CDF capital F. We're told to assume that f is invertible, but not differentiable. In part A of this problem, we want to find the distribution of a random variable yi defined to be capital F of the random variable xi. So we're plugging a random variable into a function, which is again something random. Note that yi being defined as a CDF with something plugged in takes on values between 0 and 1 inclusive because a CDF is a probability. It's a cumulative probability, but a probability nonetheless. At this point, you might be thinking of using our G-inverse formula. If you were to do that, you're going to find yourself stuck at some point with not enough information. This was the entire reason I told you not to assume that capital F is differentiable. It was to steer you away from using the G-inverse formula. But again, you could try it and you will find you do not have enough information. So let's try to go for the CDF for capital Y sub I. This is, of course, the probability that y sub I is less than or equal to an argument little y. The only thing we know at this point is that capital Y sub I is capital F of capital X sub I, so let's plug that in. Because we can assume that f is invertible, I want to take the inverse on both sides of this inequality. A CDF is in general a non-decreasing function. It is accumulating probability, so it's either increasing or staying flat, but it's never decreasing. However, in the case where we assume that capital F is invertible, we know it can't be staying flat, and it is in fact strictly increasing. If capital F is strictly increasing, then capital F inverse is strictly increasing as well. So if we put capital F inverse on both sides here and simplify, we end up with the probability that capital X sub I is less than or equal to this expression. This is the CDF for X sub I evaluated at this expression. In other words, this is capital F of capital F inverse of Y, and we get cancellation to get down to just this little y. The PDF for capital Y sub I is the derivative with respect to y of this CDF, which is 1. And again, recall that the y argument here is between 0 and 1 inclusive. From this PDF, we recognize that y sub I has a uniform distribution on the interval from 0 to 1. This is our usual notation for such a uniform, but it's fine if you want to put square brackets in here. In part B, we want to find the distribution of the quantity -2 times the sum as I goes from 1 to n of the natural log of the CDF for x evaluated at x sub I. A simplifying step would be to use the fact that we already know that the distribution of capital F of capital X sub I is uniform 0, 1, and we already have a symbol for it. I'm going to rewrite this with a capital Y sub I, and each y is uniform 0, 1, and because the x's were independent of each other, the y's are also independent of each other. So in fact, we have that y1 through yn are IID uniform 0, 1. The next natural step to take might be to look at the distribution of this thing in here, and then see if we can then find the distribution of a sum of things and go from there. So let's try it. What is the distribution of z sub I, where this is defined to be the natural log of y sub I? This one is a G-inverse problem. We've got z as some function g of y, which is the natural log of y, so y, which is G-inverse of z, is e to the z. Our G-inverse formula relating the PDF for y to the PDF for z looks like this. You can make this z sub I and this y sub I. Because all the z's and y's are IID, I chose to leave off the subscripts. This is the PDF for the uniform 0, 1 distribution. It is simply an indicator on the interval from 0 to 1, and we're going to plug this function into that indicator. we're also going to throw the derivative on the end. To simplify this, let's first consider the values in the indicator. If e to the z is between 0 and 1, taking the natural log all the way across, we see that z is between minus infinity and 0. This means that our PDF for z, or z sub I if you want, is e to the z times the indicator that says that z is from minus infinity to 0. This is not a nice, known, named distribution, but it looks kind of familiar. I just wish we had a negative up here and the interval from 0 to infinity here. We did get to choose our z sub I. We chose it to be the log of capital Y sub I. So let's choose it a little bit differently so that we get something better here. Let's take our capital Z sub I to instead be the negative of the log of Y sub I. While we're at it, let's take care of that 2 that's in front of the whole problem. So let's define Z sub I to be negative 2 times the log of Y sub I, and do the G inverse formula thing again. If Z is G of Y is negative 2 times the log of Y, then solving for Y, we get G inverse of Z to be e to the negative Z over 2. Plugging this into our G inverse formula, we end up with an expression like this. We can simplify this indicator in the same way we did before. We can put this expression here between 0 and 1, take a natural log all the way across, and then finally multiply across by negative 2. Watch for flipping inequalities. We will get that this indicator is equivalent to saying that z has to be between 0 and infinity. So rewriting this line, we end up with 1/2 e to the minus 1/2 z times an indicator that says that z is between 0 and infinity. And this means that our z sub I has an exponential distribution with rate 1/2. And in fact, z1, z2, z3, these are IID random variables. They all have the same distribution, and they inherit independence from the independence of the y's, which came from the independence of the x's. In conclusion, this is the expression we care about. We rewrote it like this because we defined y sub I to be capital F of x sub I. We then defined capital Z sub I to be negative 2 times the natural log of y sub I. So really we want the distribution as I goes from 1 to n of the Z sub I. But Z1, Z2 up through Zn are IID exponential rate 1/2 random variables. And we know that when we sum IID exponentials, we get a gamma distribution. The first parameter of that distribution is the number of exponentials we added together, and the second is the rate parameter for the exponentials. Technically, we are done with this problem. You have a correct answer and you can move on. But depending on when you saw this problem in relation to the corresponding videos, you may or may not know that this distribution actually can also have a different name. The gamma distribution with parameters n over 2 and 1/2, as we have parameterized the gamma distribution in this class, is a special distribution. It is also known as a chi-squared distribution with n degrees of freedom. N is a positive integer, and for now, you can just think of it as a parameter. I don't want you to worry at this moment what degrees of freedom means. So if x has a gamma n over 2 comma 1/2 distribution, we say that x has a chi-squared distribution with n degrees of freedom, and we write that like this. We saw something almost like this in our final answer for part B. Because our quote-unquote statistic has a gamma distribution with parameters n and 1/2, to get it into a form like this, we could write this as a gamma distribution with parameters 2n over 2 and 1/2. Now matching up this and this, we see that this has a chi-squared distribution with 2n degrees of freedom. So an alternative answer to part B would be to say that this statistic has a chi-squared distribution with parameter 2n.